Okay, so it's 5:20 and 4 out of 7 you're here. That's great. But now that I'm in under the recording, I wanted to go ahead and let you guys know I opened test 4 and practice test 4, which is on chapters 27 and 28. Test 4, of course, is another online test, and you get to use all your Google resources, your notes, your books. You can use anybody's notes, anybody's books. The only thing you're not supposed to do is use anybody's notes that were created since the test has been open, which was open today. So you shouldn't be using anything that was created on October 6th or later. Okay, that's just so someone couldn't go in and take the test, write down what they saw on it, and then give you the answers, or post it on a website, or send it a text, or whatever. So other than that, you can use any book you want. You can Google answers. The big thing is, remember, you only get a few minutes per question, and if you have to look up more than one or two, you're probably going to run out of time. And if you run out of time, it's going to be a huge penalty. So just don't do that. But that is on chapters 27 and 28. And like always, it'll have the potential to have some material from earlier chapters as well. Today, we're actually working on chapter 28. So actually, what am I doing here? Okay, yeah. Today, we're actually working on, I'm double checking the numbers because I'm teaching out of 2 different books right now. And that gets really confusing as what types of problems or what types of subjects are covered by what chapter numbers. So yeah, okay, yeah, we're on 28 now. And actually, last time I discussed a little bit about 28, because 28 is called the sources of magnetic fields. And I talked about basically there being 2 sources, current or magnetic materials, or ferrous, paramagnetic, and diamagnetic. And hysteresis, I mentioned a little bit about. All that's towards the end of chapter 28. So that's just conceptual stuff. There's also some very specific applications: magnetic circuit breakers, magnetic materials, magnetic field due to a single moving charge, some of that kind of stuff, and magnetic dipole field. So we're actually going to go over that as well. But I'm going more for right now the law of Biot-Savart, and I'm going to go over Ampere's law, force between 2 parallel wires, and stuff like that. You'll notice I don't always cover, at least in great detail, every section, and I don't also necessarily use the examples that the book does, because I figure the one that the book has are actually written really well and have a pretty good description of what they're doing. So I try to provide other ones, or I provide ones that are very, very similar to the ones in the book, only it's me doing it and solving it the way that I've found to be most helpful. So just remember that basically, unless I tell you otherwise, all the sections are covered, whether I cover them in class or not. So you want to make sure you read them all. I do try to stay away from the stuff that I didn't actually cover in detail, but sometimes some stuff is just really simple. Like, if I didn't ever cover the equation C equals Q over V, you having read it, I wouldn't have mind asking you, what is the capacitance of objects that holds 40 microcoulombs with a voltage of 12 volts? That's a pretty chucker problem, so I expect that to be okay. So I don't always do all those examples, but I try to show you the harder ones, because those are the ones that give people trouble. So we do have a test. It's open now. It's not due until the 16th, so you have till a week from Sunday, or actually for you guys, it's Monday. So it's a week from Monday for you, which is the 17th, not the 16th. So make sure you get that done. You can also look at last week's or last time's video to see some more material about the ferromagnetism, the paramagnetism, and the diamagnetism. So we've still only got 4 people in here. Does anyone have any questions now that I mentioned that stuff? Because otherwise, I'm just going to jump right into the material. Okay, well, let's jump in. So what I did in my lecture, and it sort of worked out pretty well, but I'm not confident it was that good, so I'm going to avoid doing it here. What I did was try to motivate them like I did you guys with Coulomb's law. Remember, we did Coulomb's law, and then we made the electric field for Coulomb's law. And then I tried to get you to come up with the actual vector that was parallel to the Coulomb force due to a particular particle at a particular point and at a particular point in the field. Remember, we had the vector that pointed to the infinitesimal charge element dq, and then we had a vector that pointed to the point P, which is where you wanted to know the electric field. And then I said, well, what actual vector is parallel to the line of force that Coulomb force is creating. So I sort of did the same thing, but it was a little convoluted and complicated for students to get. So I'm probably not going to delve into that, but I'm just going to jump out with the law of Biot-Savart as if it was handed to us by God. And in some sense, it was handed to us by the gods of electricity and magnetism who were smart enough to come up with this expression that actually works. Now, the problem is there's not a lot of problems you can solve with this because it's really complex calculus being done. It's literally an integral with a cross product in it and all sorts of mess. But if you take, the book Numerical Recipes in C, which, by the way, there's versions of Numerical Recipes in C, Numerical Recipes in Pascal, Numerical Recipes in Fortran. Those are some of the greatest books on how to write code to solve equations. And then you can just use that material and that information to write out integrals and work those out as well. So let's go ahead and jump in. So the law of Biot-Savart. Oh, I already started off with writing low. Law.
Share the screen.
Yeah, thank you. I don't know why it's not just automatic. Why doesn't it just fix itself? No, it doesn't. That's not the way that works. I'm so old. Y'all can call me Dr. Nefaria. All right, here we go. Okay, it looks like it's working. So this is called the law of Bio. Actually, forget that I dotted there. Savart. And it basically says that the differential element of the magnetic field is equal to mu 0 I over 4 pi times dl cross, and now I'm going to say RP minus RDL. So this is a version that your textbook does not have, over RP minus RDL magnitude cubed. And what does that mean? So let's imagine, for instance, there's a space right here. And there is, in fact, somebody just came in or trying to come in. There is, in fact, a chunk of wire carrying current like this, say. And let's say the current is coming in that way, okay? What you want to do is you would like to have, say, I've actually drawn nowhere good for this to be put, but a little differential element of length right here, whose length is dl, and whose vector dl is tangential to the line along the current. Notice it's actually pointing in the direction as the current. Now there is a vector that points to that we call the vector r sub dl. Okay. Now let's say you want to know the magnetic field right there at that point. Okay. Well, that's going to be a point P, and there's going to be a vector pointing to it that's called RP. Okay. So RP minus RDL is a vector that starts at DL and ends at P. Okay, so that's the key point here. And as you'll see, this actually works out to give us a magnetic field with the characteristics that we've seen according to the right-hand rule. Which, remember, the right-hand rule said, hey, take your right hand, grab a wire. Okay, don't get yourself shocked, but grab a wire such as your thumb is pointing in the direction that the current wishes to travel. Okay, so if the current's going up, you're going to stick your thumb up. If the current's going down, you're going to stick your thumb down. Now, if you look at that wire from, say, above, you can see your fingers curling around the wire in a particular direction. So if for instance, the current's going up and you get up over top of the wire like this and look down, you'll see that your right hand fingers are going around counterclockwise as seen from the direction the current is headed. That means the magnetic fields will be uniform on any concentric circle of fixed radius. So basically, if you go out, 1 inch from the center of the wire and make a circle, the magnetic field will have a certain strength there on that circle everywhere. The same strength, it will have the same strength everywhere on that circle. If you go out a distance of 2 inches, there's going to be another circle whose radius is 2 inches, and all the magnetic field will have exactly the same strength everywhere on that. But of course, it'll be, pointing tangentially to that circle. But in fact, that magnetic field is going to be a little weaker than the one at 1 inch because it's turns out to be inversely related to the distance. Now, we did learn when we studied electricity that a infinite line of charge gave us a electric field that was inversely proportional to the distance by itself, not distance squared, whereas point particles did distance squared. In this case, it turns out, since this is an infinitely long line of current, it's going to also vary. The magnetic field strength is going to be inversely proportional to just R, not R squared. So that's sort of a neat little sidebar to let you see the similarities. And in fact, you see that this looks like a 1 over R cubed law with that 3 exponent in the bottom. That's because what we'd really like to do, and this is what your book did, is we'd like to take that vector RP minus RDL and make that a unit vector. Because if it's got a dimension to it, a size to it, then if I multiply that by the formula mu 0 I over 4 pi times DL, then it's going to be increased by the magnitude of that vector. So in order to introduce a unit vector, you multiply it by a vector and then divide it by that vector's length. So if you think about that as one of those 3 being used to make that top vector a unit vector, then you see it's a 1 over R squared law. Okay. So let's see.
What happens if the wire that's carrying the charge is not uniform in, circumference, like an I-beam that gets struck by lightning or something?
Yeah, so if you had to do something like that, you would actually break up the I-beam, say, in little pieces small enough that they didn't have the current density. Remember, J, that we learned before, that current density wouldn't change very much over its entire shape. And then you sum up all those little pieces using just this law. The key thing to using this law is, like I said, you got to remember that DL has to point in the same direction as the current I, and it's going to be tangential to it. Okay, does that answer your question well enough?
Yeah, I guess.
Yeah, it would be a lot more complicated if it's something that's finite. Luckily, we consider in these problems just infinitesimally thin wires, or at least we're acting like they are. Okay. So as our first example, let's draw a coordinate system again, and I'm going to draw it only in 2 dimensions. Okay. So this will be our x-axis, say. I forgot that already. So this will be our x-axis, and this will be our y-axis. And what I'm going to do is imagine an infinitely long wire. Dang it. Imagine an infinitely long wire whose center is the z-axis. Okay. So this goes on for, okay, now you're making me mad. I'm just being stupid. This goes on for infinity this way and goes on for infinity this way. But the main thing is that there is a current I going upward. Okay. Now, what I would like to know is specifically out here at a distance, let's say R, this would be the point P that I talked about. I would like to know B at P, what is that equal to? Okay. So that's the problem. How do we solve it? Well, here's the solution. So first off, I got to identify some vectors. So one vector I'm going to identify is RP. RP is supposed to be a vector that points from the origin to the actual point at which we wish to know the magnetic field. So I'm going to say RP is in fact this vector right here. And therefore RP, anybody want to guess what RP is?
Is it R?
Mm-hmm. Times what? To make it a vector.
I hat.
There you go. That's it. Okay. Now, what I'm going to imagine also is there's a little differential element right there, DL. And I'm going to call that dy j hat, because the j hat's the positive y direction. That happens to be the same direction as the I is going. So that's our DL we're looking for. Now, I also need a vector that points from the origin to DL. Can anybody tell me, say, what that vector is?
Y j hat.
Exactly. Y times j hat. So this will be R, dang it. This will be RDL. Okay. And you said RDL would in fact be YJ hat, and that's exactly right. So we've got RP, we've got RDL, and we've got DL. Now we got to compute RP minus RDL. That's actually really easy. RP minus RDL, which, by the way, you can draw on here. I will draw it in, say, green. That is RP minus RDL. Okay. So RP minus RDL is clearly R I hat minus Y J hat. And I think you can see that the magnitude of RP minus RDL. Anybody want to take a poke at that?
R squared plus Y squared square root.
Yeah, square root of R squared plus Y squared. Exactly. Okay. So what we know is B is equal to the integral of dB, which according to the law of Biot-Savart is mu 0 I over 4 pi times the integral of dl cross RP minus RDL. So dl is dy j hat. We're going to cross that with r I hat minus y j hat. And then we're going to divide that by the cube of the magnitude of RP minus DL. So that's going to be R squared plus Y squared to the 3/2 power in the bottom. Okay. And technically, we're going to have to integrate this from Y approaching negative infinity to Y approaching infinity, because the wire is supposed to be infinitely long. Again, I'll remind you that in physics, infinitely long sounds like we're making a made up solution that doesn't help anybody. But in fact, we found that if R is, say, 1 centimeter, then as long as the wire, as long as you're looking at the magnetic field next to the center of the wire by about 1 centimeter away, then if the ends of the wire are maybe 5 centimeters up and or let's say 10 centimeters up and 10 centimeters down, so it's 20 centimeters long, that's probably enough. If you did 100 centimeters up and 100 centimeters down, that would really be a lot better, and that would probably bring the error down to around 1%. So it's not as horrific as it sounds. We're not making up stuff and solving problems that can't be applicable. All right. So what I'm going to do now is actually compute what the cross product is, and I'm going to say this is mu 0 I over 4 pi, and I'm going to take the integral and just write it there. I'll leave the range of integration off now. We're going to be doing a change of variables anyways. So if I take the dyj hat and cross it with that other vector, it's just a distributive property. So the dyj hat has to cross with the ri hat, and then it has to cross with the negative yj hat. So I'm going to do it one at a time. Because the cross product is a linear operator, I can pull the dy and the r out in front, and I'll get r dy. And this first part is going to be j hat cross I hat. And then the second part is going to be minus, in this case, it's going to be y dy, and then it's I hat. Oh, that first one's supposed to be j hat cross I hat. I did get that one. The second one's supposed to be j hat cross j hat. So you can actually do your cross products that way. You can just pull the magnitudes of the vectors or the vector components out in front, and then just do the cross product with the actual unit vectors, and that's just fine. This is going to become r squared plus y squared to the 3/2, so nothing changed with that. Now what I'm going to say is this is all equal to mu 0 I, and I'm going to take that first derivative, that first integral, the r dy j hat cross I hat. I'm going to work that. So the r is a constant. I'm going to put that out in front, and then put the 4 pi down here at the bottom. And then I'm going to have the integral. And what I'll do is put it in curly brackets so we know we got 2 integrals to do. So now I'm going to say this integral is in fact.
Wait, do we have 2 integrals? Isn't j hat cross j hat
exactly
0?
Yeah, we just haven't got there yet. But yeah, you're absolutely right. So yeah, anytime 2 vectors cross and they're parallel, then that's going to be 0. And so yeah, that second integral is not going to happen at all. This first one, we're going to have to do j hat cross I hat. And if you look at an XYZ coordinate system, you'd see j hat cross I hat points in the negative k hat direction. So I can stick a negative in front of here, this, and then just put a k hat right here. And since I'm using the famous k hat, I don't have to do any calculus on those at all. I hat, j hat, and k hat are truly constant vectors. They can be pulled inside and outside of derivatives and integrals all day long, and nothing happens to them. So j hat cross I hat gave us negative k hat. Y'all should verify that yourself. And then that would be over r squared plus y squared to the 3/2. Now the other part, like you were pointing out, is negative integral y dy j hat cross j hat is 0 over r squared plus y squared to the 3/2. So absolutely, this part is just 0. We don't have to toy with it anymore. Okay. So what I'm going to do now is I'm going to make a substitution, and I'm actually going to make a trig substitution. And oddly enough, it happens to be the exact same trig substitution we had to do when we were calculating the electric field due to a line, infinitely long line of charge. You know, we had a charge per unit length lambda and that sort of thing. It's the same substitution we did there. So I'm going to say, let y equal r tangent theta, then dy will equal r secant squared theta d theta. Okay. Not only that, y going to infinity implies theta goes to pi over 2, and y going to negative infinity implies theta goes to negative pi over 2. So we can go ahead and change variables completely and change the range of integration. So when I do that, I'm now going to have, don't forget, we had a negative in there and a k hat. So I'm going to say negative mu 0 I r k hat, I'm going to put right here over 4 pi. And now I'm going to have the top becomes dy is r secant squared theta d theta, and the bottom becomes, I go ahead and factor out the common r squared that will be in both terms, and it'll be 1 plus tangent squared theta, and all this would be to the 3/2 power. Okay. Now you probably, hopefully remember what 1 plus tangent squared is.
Is it secant?
It's secant squared, but yes.
Secant squared.
So 1 plus tangent squared theta is equal to secant squared theta. Not only that, r squared to the 3/2 power is just r cubed. And that did not turn out very well. Let's see if I can do this.
Isn't secant squared also to the 3/2 power? So it should be secant to the 3rd.
Yes, that's also going to come out that way. So since we saw that, I'll go ahead and since you said that, that's good. We already have it on record formally with the recording. So it's negative mu 0 I. We have an r up there already, and the k hat out here. And now on the bottom, I'm going to have 4 pi. And then notice I have an r cubed on the bottom. And not only that, there's another r from the secant squared, so that should actually be r squared on top. So now I have the integral of secant squared theta d theta over, as you said, 1 plus tangent squared is secant squared, and secant squared is to the 3/2 power. That's going to be secant cubed. So those all cancel out, leaving a secant in the bottom, but 1 over secant, I think you all know, is, anybody?
Cosine.
Cosine. So I now have negative mu 0 I over 4 pi r. That's the only one that existed. K hat integral negative infinity to pi, or excuse me, negative pi over 2. So pi over 2 of cosine theta d theta. Okay. Now you know the derivative of sine is cosine, so the integral of cosine is sine. We know the sine of pi over 2 is in fact 1, and the sine of negative pi over 2 is negative 1. So this is going to be sine of pi over 2 minus sine of negative pi over 2, which is 1 minus negative 1, which is 2. So this whole integral right here just becomes 2. So ultimately what we see is B is equal to mu 0 I over 2 pi r k hat with a negative. Okay. And that's sort of the answer, but I'm going to do some explanation of it in a second. So that's sort of the answer. So let me stop sharing just a second to explain what I mean. So what we had was a y-axis and an x-axis, like this or whatever, and a current going upward. And over here on the x-axis, it pointed into the board, into the page, right? But if you rotate that coordinate system 15 degrees, say, then you go back to the side, whatever, in the same way that the x-axis was originally pointing, that vector B is still going to point into the page. And if you rotate it, 15 more degrees, it's still going to point into the page. So you see it always points tangentially outward, or excuse me, tangentially along a circle of radius r. So I would actually argue that the best interpretation is realizing that this is B equals mu 0 I over 2 pi r, oh, not that one, times the theta hat vector in polar coordinates. Okay, and that's just because of the symmetry of the problem. It actually allows you to consider that at every position in space, rotating as if the z-axis is the axle. You rotate it, it's always going to point in to the right of it. So if you're looking at the x-axis, you're actually meaning the vector that points vertically with the x-axis vertical, or in this case, the y-axis vertical. And as that rotates, that ends up becoming, instead of like this, which is when it's on the x-axis, it goes like this, and it gets to the y-axis, and it goes like this as it gets to the z-axis. So if we actually place this along the z-axis instead of the y-axis, you would see that it is actually the theta hat unit vector. Again, that theta hat being from polar coordinates. So let me just refresh you on what that is. Again, this is beyond what's necessary, but it allows me to use these words and these symbols, theta hat and r hat and phi hat and all that stuff. It allows me to use them with you having some knowledge of what I'm talking about without having to do the extra work. That being said, if you actually do the extra work, it'll help you immensely when you take your dynamics class, when they give you that Coriolis force and the omega cross r force and all that stuff. That looks like Greek and you're just going to plug and chug it. But if you realize that in spherical coordinates, the r position vector is just r of theta, phi, and r, the distance, as a vector function. Okay, so you can write that out in terms of some r of t times the r hat vector for spherical coordinates. And since the acceleration is the second derivative of that position vector, you actually have to use the chain rule repeatedly on the thetas, the phis, and all that good stuff, and the time, of course. And that's where all those extra terms come from. It turns out the Coriolis force, the omega cross r thing, those are actually just terms in the acceleration as a result of you studying a reference frame that's spinning. Okay, so let's leave that for a second, just reminding you that. But let me draw a coordinate system that is in fact polar. Okay, so first off, we'll talk with the polar, and the only difference between polar and cylindrical is the polar leaves off the z-axis. So if you're doing cylindrical, you just have polar with a z-axis sticking out of the origin. So let me do this. I'm going to draw a coordinate system like this. Okay, this is going to be my x-axis. This is going to be my y-axis. And in fact, we might have a point right here that we could call P, say. Well, that, of course, has a coordinate of x and y. So P means x comma y, which this would be your x and this would be your y. But in cylindrical coordinates, or in this case, polar coordinates, it's also a coordinate r comma theta, where r.
Are you supposed to be seeing what's on your screen?
God, I did it again. Thank you. Thank you very much. What is wrong with me? I'm like, just clueless. Sorry, folks. Hold on. Okay. Yeah, you were supposed to see. Thank you for being gentle about my my mental issues. Let's call it that. I know some people get offended by the R word, so I didn't want to use that, even though my sister has that problem. So I'm not meaning it in a disparaging way, other than laugh at myself. So there you go. What I drew was the x-axis, the y-axis, and the point P. As you can tell, since it's directly above x and directly to the right of y, the coordinate is x, y. But I'm saying in polar coordinates, this could also be the distance r. And this right here could be the angle theta. So it turns out in that world, there is some nice coordinates that you can use. And just like I hat points in the direction of increasing x, and j hat points in the direction of increasing y, and k hat points in the direction of increasing z, r hat is going to point in the direction of increasing r. But it's a unit vector, so that's r hat. And then theta hat, we're going to actually make a rectangular coordinate system that has basically three mutually, or in this case, two mutually perpendicular directions. So the way that theta increases is going this direction, and that's going to be in fact theta hat. So that's what those vectors are. You could tag along with that and realize that this is a right-handed coordinate system if the z-axis is coming out of the page, and then of course the k hat would be coming out of the page at that same point as well. But with a little analysis, you can see that this angle right here is theta. And if I was trying to find the y and x component of that, what I would say is r hat is equal to the magnitude, which is 1 times the cosine of theta times I hat. That's the X component. And then you'd see that it's going to be plus 1 times the sine of theta j hat. So in fact, r hat is just cosine theta I hat plus sine theta j hat. And now you know, if you obviously you took the sum of the squares of that, you're going to get sine squared plus cosine squared. And we all know that sine squared plus cosine squared is 1. So it is a unit vector as we expected. Now, the other part is you can take this little vector, the theta hat, and realize that this angle is theta as well. So theta hat becomes, again, remembering it's a hat, so its length is 1 again. But in this case, you can see that the y component, or excuse me, the x component is going to be negative, and it'll be negative of the sine of theta. And I just left off writing the 1 because I knew it would disappear anyways. So I'm going to say negative sine hat, theta I hat plus cosine theta j hat. And that's what those coordinates are. That's what those little unit vectors are. Okay. You could do the same thing with polar coordinates, or excuse me, cylindrical coordinates. The only addition would be you just add a k hat to it, and a k hat's automatically k hat. You don't have to do anything. But if you did it in spherical coordinates, you could do some wonderful stuff too. And that's what I'm talking about when you go to take the derivative of a position vector. Just quickly, let me show you what that unit vector sort of thing would look like in that world. So let's say we had this, and this, okay? If you wanted to find a point in space, say right here, what you could do is you could go straight down from it. Whoa, didn't mean to do that. I want to go straight down from it until it hits the XY plane, because this is going to be X, and this is going to be Y, and this is going to be Z, okay? Now I look at where this hits the X-axis. I still need red here. And then I look at where this hits the Y-axis, and that would be my X. That would be my X value, that would be my Y value. And this we could call this quantity from here to here, which is the projection of R in there. We could call that, for instance, rho. And alternatively, what we could do is say this angle right here is going to be the azimuthal angle theta. So now we're talking about polar coordinates. I mean, the same as polar coordinates, but we're actually talking about spherical coordinates. This line right here has a length R. And I did that without a nice straight line, so that made me mad. Okay, that has a length R. And then we'd say, okay, well, there's also an angle downward called the polar angle, and that's phi. So this point, which is now moved, and I don't know why, but it did, so we're going to pretend like it didn't. We're going to say,
isn't the azimuth angle from horizon up until the point? Like if you're shooting an azimuth on a ship to, like, you know, celestial locate yourself,
right?
You would be shooting at a star from the horizon. So the azimuth angle is from the horizon, not from positive X to the sweeping angle. It'd be from the horizon to the point.
No, you've got the coordinate in a different orientation than we generally do. So what we see is the y-axis is due north, the x-axis is due east. And then your azimuth, y'all might actually—
right, but the azimuth angle should be from the XY axis is your horizon. The XY plane is the horizon. The azimuth angle should be between rho and R. from what
Yeah,
I
not,
understand.
not the way we do it in math. It might be that way. I have a Navy maneuvering board. I should probably, I mean, book, and I should probably check it out. But in math, we use it this way. So we use the polar angle as coming down from the pole, and the azimuth angle is like our 30 degrees east of north, that sort of thing. So it's actually measured from Y as opposed to from X when we're talking about compasses. But in the coordinate system, we measure it from the positive X towards the Y, so that it matches just like our polar angle. Does that make sense?
I guess so.
Okay. Yeah. So it might very well be different from what you're used to in the Navy, or I assume the Navy or Air Force or whatever. But anyways, this point would be X, Y, Z. And you can see that, of course, because if you follow this over, dang it, what's that? That was really weird. Never saw that happen. So if you follow this like that, you'd see that that's the actual Z. So it's X, Y, Z, but it's also the same thing as R, theta, and phi. And you can see, for instance, rho is something we absolutely need. We know, for instance, that Z is equal to R cosine phi, and that rho is equal to R sine phi, but X is actually equal to rho cosine theta, and Y is equal to rho sine theta. That means this is R sine phi cosine theta, and this is R sine phi sine theta. So that's how you convert back and forth to all those. And of course, the R vectors, the R hat vector would actually have components that look just like this. It would have a Z component that's just cosine phi, and it would have an X component that's sine or cosine theta sine phi, and then a Y component that's sine theta cosine phi or sine phi again. So that's where all that stuff comes from. So that's spherical coordinates, just for the record. Now, what I'm going to do is I'm going to show you another version or another use of the law of Biot-Savart. And there's very limited exercises that we can do on this. So we're just going to have to do that. And you'll see there's a lot of variations you can make. So I'm just making up one from scratch, and it's going to take up a big page. So I'm going to go ahead and advance another page. So what I have, or what I'm going to try to have, is I'm going to have a coordinate system like this and this. And I'm going to say this is my x-axis and this is my y-axis, and this is let's say our wire is going to come right along here this way, and then actually it's going to come right up to here, and then it's going to make an arc from here to here. That's supposed to be a quarter of a circle, even though it doesn't look that good. And then it's going to go up to here and make an arc of a quarter of a circle again. And then it's going to come out this way, so that my current, dang it, it didn't change that. So that my current is actually going this way, this way, this way, this way, and this way. Okay. What I'd like to do is find out the magnetic field B at P. Okay. So that's the whole process. And what I'm going to do is I'm going to assume that this distance from here to here is just plain R, and this distance from here to here is plain big R. Okay. So I've got a couple parts here. I've got part 1, part 2, part 3, part 4, and part 5. Okay. So let's start with part 1. So this is our solution. Part 1 what I'm going to see is that RP, and actually RP for all of them is 0, because it's supposed to point from the origin to the point where you wish to know the magnetic field, which is at the origin. Okay. So that's going to be 0 for all of them. Now, in this case, I'm going to make this into DL. So in fact, DL would actually equal to, notice it's got to go in the direction of the current. So I'm going to have to put a negative in front of it, and I'm going to call it DX because that's the variable who's changing. And it's going to point in the negative I hat direction. I wrote J because I'm dyslexic, I guess. Okay. And that's negative DX I hat. So that's what DL is. RDL, anybody want to take a poke at what RDL is? Let's just say its magnitude is X, and obviously it points a distance X from the origin into the I direction, so, or into the X direction. So that's it. So now I've got RP minus RDL, which is what we need for.
Wait, doesn't it have to go in the I hat direction? Since it has to, DL has to go along with the current, right?
Right. That's why
current is pointing in the negative I hat.
Yeah. So that's why the DL is pointing, has a negative on it, but the RDL just points from the origin to where DL is. So DL is on the same distance X. Does that make sense?
Yes, it does make sense. It's just a positional vector. It's not a
exactly. It's not DL vector. Okay. All right. So RP minus RDL is just going to be negative X I hat. And you can see something already on that, specifically the DL cross RP minus RDL is going to be proportional to I hat cross I hat, which equals 0. You see that?
Yes.
Okay, so 1 doesn't have any bearing on it. You can also see that 3 is going to have RP equal to 0. It's going to have DL equal to DY J hat. And it's going to have RDL equal to Y I hat, or excuse me, Y J hat. So again, DL cross RP minus RDL is going to be proportional to J hat cross J hat, which is equal to 0. So anytime you have a radial line and you're actually calculating the magnetic field at the origin, all of those radial lines are going to give you a magnetic field of 0. So I can also go over here and do number 5. And again, RP is equal to 0. RDL, actually not RDL, I want to do DL first. DL is going to be equal to DX I hat in the negative direction. And then RDL is going to be X negative I hat, or negative X I hat. So again, DL cross RP minus RDL is going to be proportional to I hat cross I hat, which equals 0.
So the magnetism of any wire pointing into or pointing out of P is 0.
Yeah, in other words, magnetic field is always perpendicular to the vector that connects those, so you can't get any magnetic field there, basically. I think I said that mixed up, but I think hopefully you understand what I was saying. So if the line or if the current is headed towards the origin or away from the origin will have a 0 magnetic field due to that thing. that part of the current.
What if point P was sitting on point 1 in the middle of the wire?
Okay, then yeah, all bets are off, and you're going to
Because
get a
the
nasty
rate,
thing.
because the magnetism gets what?
Yeah, yeah, you would have a mess. It'd just be a hard one to work.
All right, but if the magnitude of the magnetic field gets stronger as you get closer to the wire, what happens when you touch the wire or get inside of the wire?
If you actually put the P at, say, right where that little green arrow is in part 1, okay, you're actually going to have a magnetic, actually, you wouldn't have any vector right there. I mean, you wouldn't have any magnetic field right there, but if you go up a little bit above it, you would have a magnetic field pointing into the screen. If you go down a little bit, you'd have a magnetic field pointing out of the screen. If you went instead of up or down, but came out of the board, but still aligned with that arrow's head, you'd have a magnetic field pointing up. And if you went behind that arrow, behind the screen, you'd have a magnetic field pointing down. But along that axis, you're not going to have any magnetic field.
So the magnetic field gets increasingly and increasingly stronger the closer you get to it, but once you are to it, it becomes zero.
It was sort
Just
of
indeterminate.
It becomes indeterminate.
Got it.
Okay. Yeah, that's a tough question. Is this Nathan or who's just talking? That didn't sound like Nathan's
Nathan.
voice.
Yeah.
It is Nathan. Okay. All right, gotcha. So now let's do part 2. So fun, right? Now part 2 is actually where stuff gets interesting. So what I'm going to imagine as DL is in fact going to be this little smudge to this little smudge. And of course, this angle right here is theta, but this angle is d theta. So I'm going to say that RP again is just 0 because that's the vector that points from the origin to the point that you wish to know the magnetic field, but that point is the origin, so it's a 0 vector. Now DL is actually going to be R d theta long. And to make it point in the right direction, I got to put it in the theta hat direction, which is why I took the time to show you that theta hat stuff earlier. Okay. The DL would in fact point this way. Okay. Now RDL is actually going to be just R hat, because that's supposed to point from the origin to DL, so just a length R. But remember, R is a function of theta, so it's not like we're just saying how far away it is. We're actually given the angle theta too, because R hat has a definite theta dependence. Okay, so now we can say RP minus RDL is actually equal to negative R hat. So B, which equals the integral, or excuse me, which equals mu 0 I over 4 pi times the integral of DL cross RP minus RDL over RP minus RDL's magnitude cubed becomes mu 0 I over 4 pi times the integral of theta equals 0 to pi over 2 times R d theta hat crossed with negative R hat over, I think you can tell that the magnitude of RP minus RDL is just equal to R. So this will be over R cubed. Okay. Now, in this case, we're integrating everything with respect to R. you can see that there's going to be an r squared in the top and an r cubed in the bottom. They can all be brought out to the front. So I'm going to say now this is mu 0 I r squared over 4 pi r cubed integral d theta theta hat cross r hat. Now, in general, if this doesn't work out to something like k hat, then we'd have to go and plug in what theta hat is, plug in what r hat is, and integrate it as it stands. So right now, what I'm looking at is theta hat cross r hat is actually into the board. Remember, r hat would point diagonally up parallel to that green little r line, and d theta is shown parallel, or dl is in the theta hat direction. So you see that way. So if I do theta hat cross r hat, we get a point into the board. So that's a negative k hat. So I'm now going to write that this is negative mu 0 I over 4 pi r k hat integral d theta from 0 to pi over 2, which actually just gives me negative mu 0 I over 8 r k hat. Okay. Any questions on that? It turns out to be a really easy thing. That's the nature of it. And you can do any number of, radial lines to make sure it's a complete wire that carries one continuous current. If you want, I could, take a left at number 5, at the end of number 5, and go back and trace a arc that goes all the way back to the positive x-axis on a new radius, say 2 times big R, and then add that magnetic field to it, and that would give me the result of that new structure. So you can just keep adding on arc lengths and radial lines, and every time you'll know the radial line's not going to contribute at all, but the arc lines will. And you've got to use your right hand rules. Like you see, if I did in fact make that current go back off in the clockwise direction at radius 2r, that would actually create a magnetic field that points in the positive k hat direction instead of the negative k hat direction. So it'd actually be decreasing the effect. But let's go ahead and do now part 4. Any questions before we go on? All right, so RP is again going to be the 0 hat vector, okay, or the 0 vector, not hat. Definitely can't be hat. Okay, DL is again going to be the exact same thing as it was in part 2, only the radius is larger, so it's going to be R d theta theta hat. Okay, and RDL is just going to be big R times R hat, and then RP minus RDL is just going to be negative R hat. And then the magnitude of RP minus RDL is just going to be R. So B is going to be equal to mu 0 I over 4 pi integral of R d theta theta hat crossed with negative R hat over R cubed. Okay, and that's going to be integrated from theta equal pi over 2 to pi. So I get an R squared on top again and an R cubed on the bottom again. That can all come out in front. So I'm going to get, and then theta hat cross R hat is again going to give me a negative k hat. And I think I might have left off a negative before. Yes, so theta hat cross R hat does give me negative k, but notice there was a negative in here. So I'm going to draw something really quickly. See that negative sign? So that's supposed to be positive. That's supposed to be positive.
Wait, why is it supposed to be positive? I thought negative r hat cross theta hat should be negative k hat.
Okay, so we have a negative in front. Let's just hold on to that for a second. But we have a theta hat cross k hat, and theta hat is like this, and r hat is like that. So it's actually k hat. If we just do theta hat cross r hat, that points into the page. But when I multiply that by a negative, it actually points out. So it does. It's supposed to be
So
positive.
r cross theta would be k, but theta cross r is negative k. I got
Exactly.
it.
Yep. So I just dropped that sign when I was working out the details of it. So this should have been theta hat cross r hat is negative k. And actually, let me make that a little better. I'm not happy with that. Whoa. Okay. So in this case, the same thing's going to happen. We're going to get, and that's as you expect. You expect both of these, since they're both going the same counterclockwise direction, you suspect both of them are going to contribute a magnetic field that points in the same direction. So I'm going to get the mu 0 I over 4 pi big R, because the r squared and the r cubed cancel out, leaving an r in the bottom. That's going to be in the k hat direction. And it's going to be the integral of d theta from pi over 2 to pi. And that becomes pi minus pi over 2, which is in fact pi over 2. Also be 2 pi over 2 minus pi over 2 gives you pi over 2. So in fact, I get yet another contribution of mu 0 I over 2, or excuse me, over 8, but a different r and k hat. Okay, so now I'll go ahead and box this answer off. And now I know that B total, B at P, is in fact equal to, notice all of the terms have a mu 0 I over 8. So mu 0 I over 8 times 1 over R plus 1 over R K at is the net magnetic field as a result of that. Any questions? Okay, so I think I've got the signs that I dropped corrected too. All right, so now that we know this stuff about infinitely long wires, and I showed you how to use this law of Biot-Savart, there turns out to be a lot easier way if the symmetries are there. But first off, I want to talk about two wires that are, say, parallel. So let's imagine two parallel wires. So there's one, and there's another. And I'm going to assume this one has a current of I1, and this one has a current of I2, both going upward. And I'm going to assume that the distance between them is D. What I'd like to know is, what is the force on 2 due to 1? Notice the reading I said that. That's the force on 2 due to 1. Okay. Well, the way we can attack this is we realize wire 1 is carrying a current and therefore making a magnetic field. And we know exactly what that magnetic field is. If I grab that right wire with my right hand, my thumb pointing up, and I look down on top of it, what I would find is that the magnetic field at the wire is in fact pointing into the page. And that's B due to 1. Okay. Now that b due to 1, so this is our solution. Evidently, I'm writing it in green now. Our b due to 1 is actually mu 0 I1 over 2 pi d. Everybody agree with that? Now, at this point, you can use either F equals IL cross B, or I like to use this because I never think of that. Yeah, plus it says Bill. I like to say it as Bill when it's not in the direction that I need it to be. So it aggravates me. So I'd rather use F is equal to Q V cross B. And this actually works either way. Okay. When we talk about conventional current, like I1 is supposed to be, that means we're pretending positive charges are going up in I1 as well as in I2. So Q times V, since this Q is a positive charge, Q times V is parallel to V. So the QV is a vertical vector on the page. So if I take remember your QV is supposed to be this rod that acts like an axle, that's your pinky going all the way back, say, to your wrist. Well, I can put my hand in any of these positions as long as this is parallel to vertical, right? But I need to find the direction where my fingers can curl in the direction of B. That only happens when my palm is flat facing the screen. So now my fingers can bend in towards the page and therefore are parallel to B. At that point, my right thumb is pointing to my left. And in fact, it's saying that I2 is attracted to I1. So I'm going to say the force due to this thing is in fact this way. Okay. And notice the magnetic field is perpendicular to the current, and therefore the cross product's really irrelevant. So ultimately I can say that F21 is going to be I times L times B. Well, let's just assume that the wire, we're actually going to be more interested in the force per unit length, but we could imagine a section of wire of length L. So if I wanted to, I could go ahead and say, let's say from here to here is L. Then we'd say F21 is I2. Well, I didn't want that one. Is I2 times L times mu 0 I1 over 2 pi d, or you could say F21 per unit length is mu 0 I1 I2 over 2 pi d, and that's our result. So parallel currents attract. And you can use the same reasoning to show that anti-parallel repels. Okay. So that's a new rule that we learned, so, sort of. Okay. So now we've got 10 minutes. And what I'd like to do is introduce you to Ampere's law. So Ampere's law is not technically correct yet, but it's not going to harm us anywhere right now when I write this. But Maxwell is going to correct it, and we'll use that corrected version later on. But right now, what people found, including Ampere, obviously, because we call it Ampere's law, we found that basically, if you have a closed loop, so let's draw my closed loop like this. Okay, there's a closed loop. I can imagine integrating around that closed loop. In this direction. And it turns out that the integral over that closed loop, so we'll put a circle on it like we did with Gauss's law, because that had to be an integral over a closed surface. This has to be an integral over a closed loop. And it is the integral of B dot dl, where dl is a differential line segment tangential at each point, like that. Okay. Well, it turns out when you do that, that quantity is equal to the sum of all the currents going through that. So it's a summation. Well, actually, let me write it this way. It is mu zero times the summation over I. Actually, that's an unfortunate symbol to use. Let's say over. No, I can't use that one either. Let's say over lambda of I sub lambda. But the I sub lambdas have a rule associated with it. So if you have, for instance, imagine this loop as being the outer ring of, let's say, a balloon maker. So let's say we made a ring out of plastic that is in exactly that shape, and that's actually a flat plane. It lies in a flat plane. Now, if you took that and you dipped it into some liquid, which was basically mostly water, a little bit of glycerin, and a little bit of dish detergent like Palm or Palmolive or Dawn or whatever. Okay. If you did that and then dipped it into the water, sloshed it around a little bit, and then slowly picked it up, it would actually make a surface that was flat on it. And that surface could look like, made out of balloon, of course, or made out of bubbles, of course, would look like this flat surface there. But in reality, it could actually be any surface that is bounded by that. So all those balloon shapes that you, or bubble shapes that you could make by moving it through the air, those would be fair as well. But what Ampere's law is telling us is that every current that goes through that balloon bubble sheet that I'm writing here, let's say this is I1 going this way, and this could be, for instance, I2 going that way, and I3 going this way. In this case, it would be I1 plus I2 minus I3, because it has to obey a right-hand rule, meaning if you point your direction in your thumb and of your right hand in the direction of the current, your fingers should be curling around it in the same direction that these arrows are going. You can see that's true for I1 and I3, which I wrote backwards, cracky. You can see that that's true for I1 and I3. So this summation would end up being I1 plus I3 minus I2, because I2 is actually pointing in a left-handed direction. Does that make sense? Everybody see how that's the opposite direction? So we're imagining a path, a ring, if you will, that's closed, and all the surfaces that could be bounded by that path, all the two-dimensional surface that could be bounded by that path. Any surface that could be bounded by that, you count up all the currents going through that surface using this right-hand rule to designate positive or negative. That's going to be equal to the integral of B dot dl. So with that in mind, let me go ahead and use this as an example. First, I'm going to attack this very same problem that I started with, which was an infinitely long wire. So let's imagine a coordinate direction, a coordinate system. We'll put my coordinate system right here, and right here. That's going to be my X, that's going to be my Y, and that's going to be my Z. Okay. Now I'm going to put a long current carrying wire. That actually turned out pretty good, but it's not perfectly straight, so I'm going to OCD about it. And then here's the other part of the wire. And again, I'm going to assume that this current, I'm going to assume that this current I is going up. Okay. Now, from symmetry and what we've studied about wires and Biot-Savart law, I know that the magnetic field should be related to the distance away from Z. And in other words, if I found a circle whose center was along the Z axis and was parallel to the XY plane, I would suspect the magnetic field would be of constant strength everywhere on that circle, just from my knowledge of the law of Biot-Savart. So what I'm going to do is make a Amperian loop, is what they call it, that looks roughly like that. and I'm going to integrate around it in that direction. Okay. I'm going to say it has a radius r. This is an Amperian loop of radius r and parallel to the XY plane. So I hypothesize, I want to know the magnetic field B equals question mark. So my solution is going to start with a hypothesis, just like it did with Gauss's law. My hypothesis is that B is equal to some B that depends on R of cylindrical coordinates times theta hat. Again, cylindrical coordinates, right? You see that theta hat would actually be this direction, this direction, this direction. So it fits what I want, right? So now I'm going to say left-hand side, closed integral of B of R theta hat dotted with DL. Now my DL is going to be R d theta in the theta hat direction. So this is going to become R d theta theta hat, which ends up becoming the integral of B of R times d theta times theta hat dot theta hat. And theta hat dot theta hat is not just a cute little owl. See how it looks like a cute little owl? Now it even looks more so. It's actually equal to 1 because the dot product is the magnitude of one times the magnitude of the other times the cosine of the angle between them. That means 1 times the cosine of 0, that's 1. And in fact, R, and since B only depends on R, B of R, both of those are constants. So I'm ultimately going to get B of R times the integral d theta, which equals, of course, theta equals 0 to 2 pi. So you end up getting B of R, or actually, let me write it a different way. B of R times 2 pi R. So that's the thing, the trick. You know, you're never actually going to do an integral on the left-hand side. You're doing an integral, but you're supposed to be recognizing that it's going to be all 0, or it's just going to be B of R times some length. Okay, that's what the left-hand side should always come out to be. Now the right-hand side is supposed to be mu 0 times I enclosed. That's another way of writing it, and that's the way I'll use it from now on, even though I wrote it a little differently to explain it to you. So in this case, this current is going in the right-hand direction, so this just becomes mu 0 times I. So I say left-hand side equals right-hand side becomes B of R times 2 pi R is equal to mu 0 I. And that gives me, using my hypothesis, that the vector or the magnetic field is mu 0 I over 2 pi R in the theta hat direction. Okay. So we got the same form again. Let me quickly, just to give you a little bit more experience, and you can see examples with solenoids and toroids. I'm just going to do a solenoid real quick. Let's imagine for a second that I've got a bunch of wires that are wrapped up in like a solenoid. Okay. You remember a bar magnet that you learned about in grade school? It was basically, you could take let's say a round iron rod and you wrap wire all around it. Well, if you wrap it really, really neat, where up against the first row is the second row of wire touching it, and then the third row is up against that touching it, so it's really smooth. Well, you get the same thing when we do it here, okay? So in the top, those currents are coming out of the page, and in the bottom, these currents are going into the page. And we're going to say that it has N turns and a length L. Okay. such that N, the number of turns per unit length, is N over L. So that might come in handy as well. So I know what the magnetic field does from this. It's actually a series of very strong magnetic field lines right here in the middle that are axial. And then they come around and get really weak out here. Okay. So I'm going to choose an Amperian loop that goes from here to here to here to here. And notice I'm choosing it in a right-hand direction so that all the I's will be positive. And I'm going to say this length right here is L, and those other lengths aren't really going to matter. So the left-hand side, here's my solution. I hypothesize that B is going to be equal to B of Z I hat, where Z is, say, how far you are from the wire, okay, from the coils. And the left-hand side, closed integral B dot dl, is going to be integral from 0 to L of B of Z I hat dotted with dx I hat. That's for that first part. Plus this part right here, the second part. The second part, in fact, has a direction. The current's going to be in the direction that's perpendicular to the magnetic field, at least inside the solenoid. So the dot product will be 0. And then right between the wires, those magnetic fields are going to cancel and give you 0. And then outside of the solenoid, the magnetic field's so much weaker compared to the inside, we're going to assume that magnetic field 0. So in fact, 2, 3, and 4 all have 0, 0, and 0. So we ultimately just get B of Z. Again, Z is measured from the, say, from the axis or from the coils of wire, times L is all the left-hand side gets us. The right-hand side, though, is supposed to be mu 0 I enclosed. Well, that's going to be mu 0 times the number of wires. Well, you can get that, the number of wires, by multiplying the number of wires per unit length times the length, and then times the current the wires are carrying. These currents are, of course, currents I. So left-hand side equals right-hand side gives us that B of Z times L is equal to mu 0 N L I, or B is equal to mu 0 lowercase n times I in the I hat direction. So that's it. That's we could do a solenoid. Your book does a solenoid. I'll probably do one for you next week. But a torus. But basically, a torus is just you take that solenoid and bend it into a donut. Put the two ends together. In other words, then you'd have a torus, and you get a similar answer, but not quite as simple as this one. So that's the way you use Ampere's law. I still haven't shown you a magnetic dipole. We'll do that next time, but you guys are free to go. Of course, I ran over about 3 minutes. Obviously, whenever I run over, you're welcome to leave at any time. But I'm going to, once you guys do leave, I'm going to finish doing some of this stuff with that spherical coordinate system just because I enjoy it. And y'all might get some happiness out of it. So I'm going to do that.
I did look up that azimuth angle, and
Okay.
azimuth angle is the angle from the north in the XY plane, not
Gotcha.
the angle from the horizontal plane to the vertical. So
Good.
you were
Gotcha.
right. I was wrong. I probably just misremembered. I'm not a big
I
chart
doubt you've been
person,
doing it
so-
wrong all that time. You just probably just misremembered.
Well, I didn't do it at all because I was the guy who made the eggs.
Oh, gotcha. So you went through the course but never actually did it. That would be a very good reason for forgetting it. So yeah, I get you.
All right. I'll
Thanks,
see you next
guys.
week. Bye.
I appreciate y'all coming. Have a good one. Have a safe weekend, fun weekend, and I will see you guys next week. And ladies, if there are any in here now. Robert, did you have any questions? All right, I'm going to go ahead. Whether you're staying here or not, it's okay with me. I'm going to go ahead and finish that part about the spherical coordinates that I enjoy so much. I'm going to double check my work. Rho cosine theta is in fact X and rho sine theta is in fact Y. So I'm okay with that. And rho is of course R sine phi. So I'm okay with that. And normally we put the theta before the cosine. So let me rewrite that. I'm going to say now that I'm going to say that X is equal to R cosine theta sine phi, and Y is equal to R cosine theta, or excuse me, R sine theta sine phi, and Z is equal to R cosine phi. Okay. So from that, we can see that the R hat vector, which actually is a function of theta and phi, is actually going to be this little guy right here. And you can see that has a, since it's a hat, it is a one, it's a unit vector. So this length is 1. This angle is phi. And this angle is theta. So R hat is in fact going to be cosine theta times cosine phi. I've got that backwards on my line above it. So let me correct that too. So that's supposed to be, oh, cosine, no, that part's right. So that's cosine theta sine phi I hat plus sine theta sine phi. And there, I just noticed I copied this wrong. And this will be sine theta sine phi in the j hat direction. And then finally, the z would be cosine phi in the k hat direction. So that's what R hat is. And then theta hat would actually be in the XY plane. Actually, not that one at all. Sort of would be, you actually would be best to represent it down here. This will be, say, theta hat. And you can see that, of course, this angle is the same as theta. So theta hat as a function of theta and phi is going to be, I don't need to deal with phi at all. I just have to deal with theta. And in fact, the x component is going to be negative sine theta I hat. And the y component is going to be cosine theta j hat. And of course, you could also have a phi hat direction, which a phi hat unit vector, which would actually point this way. And that phi hat, of course, has been basically shifted by 90 degrees ahead of R. So in fact, it has a, it makes an angle phi with the Z axis. So the Z component is going to be cosine phi. And then the XY component is going to be parallel to rho. So with phi hat, it's a function of theta and phi. We're going to say it has a rho component and a z component. So first off, I'm going to say the rho component is basically rho hat is the direction. And by the way, rho hat would point, let's say, this direction, even though I'm just using it as a placeholder. It's not actually a formal thing that we're going to be working with. But to get my component that way, I'm going to basically just take and multiply the sine of phi by 1. So this would be sine, keep switching to green and forget, put it back. So this would be the sine of phi times rho plus now the cosine of phi times k hat. Now rho hat, technically, you can see here, if I take the time to draw it a little bit more, this would be my x-axis, this would be my y-axis again. So you can see that rho hat, again, you can see that rho hat would actually have components of this angle is theta right here. So it would be cosine theta I hat plus sine theta j hat plus cosine phi k hat. So finally I have phi hat as a function of theta and phi, even though you really don't use these two, generally you just use the R one. But anyways, this is going to be cosine theta times sine phi I hat plus sine theta sine phi j hat plus cosine phi k hat. So in fact, these are what you really use. So if you actually want to write a position vector in spherical coordinates, all you really have to do is write that r as a function of time is equal to r, the distance as a function of time, times r hat as a function of theta and phi. That's the whole thing. So when you go about taking the derivative of this to find out the velocity, you're going to have to take the derivative of cosine theta times sine phi times r, where r is the r of t I just drew down here, and use the chain rule repeatedly. And that's where all those extra terms like the Coriolis force, omega cross r comes from and stuff like that. They're just necessary parts of the acceleration that you experience just as a result of the actual coordinate system sort of rotating. Okay. All right, that's it. That's just a little extra. You don't need this stuff really, to be honest with you, for this class. I just need to be able to use the symbols. And every time I show you the symbols, that just gets you more familiar with it. If you actually have to reduce it to an r hat, then you know it's going to be cosine theta I hat plus sine theta j hat. Or if you have to reduce it to a theta hat, you know that's going to be negative sine theta I hat plus cosine theta j hat. So I hope this helps, and I am going to call it a day. It seems like all of my students are gone except for Robert. Robert, do you have any questions, sir? All right, I don't think Robert's still here, so y'all have a good day.